Well, thanks everyone for coming to listen to my final PhD seminar, which is about land-atmosphere interactions and their effect on Australian rainfall. I've been supervised at ANU, the Fenner School by Albert Van Dyke, and at UNSW by Jason Evans and Andy Pittman. Hopefully today I'll be able to pique your interest a bit in some of the processes going on in the landscape and the atmosphere around us that determine if and when we get rainfall. So the overarching aim of my PhD is to determine the influence of land-atmosphere interactions on Australian rainfall. And today, having a look at that, I'll first introduce what land-atmosphere interactions are and how they're measured and why they might be important, why we should care. What we do and don't know about the impact of land-atmosphere interactions on Australian rainfall, which will lead into the motivation and research questions that form the PhD. I'll then just go over the PhD in summary, the research, and we'll finish with some conclusions and potential future work. But firstly, what are land-atmosphere interactions? Well, I think if we start with the hydrological cycle, we understand that water is transported between the ocean, the atmosphere, and the land. But traditionally, each of these components has been more or less studied in isolation. But interactions occur as water and energy and chemical compounds are exchanged between these components. And between the land and the atmosphere specifically, the exchange of water and energy create complex interactions that ultimately impact the occurrence of rain. And these land-atmosphere interactions happen within the boundary layer of the atmosphere, which is the part of the atmosphere closest to the land surface. So you'll hear me talk a bit about that today. And these interactions vary from local to global scales and can vary in strength seasonally and even daily. So for example, when it rains, the soils and the vegetation receive moisture. Some energy is used to evaporate that water back into the atmosphere, changing the temperature and humidity and other profiles of the boundary layer, other properties rather, which affect the potential for rainfall. And when we get rain, it wets the soil and so on and so forth. The cycle goes, creating a feedback. And there's other examples of feedbacks between the land and the atmosphere. For example, on a nice sunny day when there are a few clouds around, the land surface heats up and the sensible heat energy is used to heat the air in the atmosphere above, which causes the boundary layer to grow in height, where it can mix with the air in the upper atmosphere that may be cooler and drier. And this again changes the atmospheric properties to affect atmospheric pressure and winds, which can affect how much moisture is evaporated from the surface, which also affects how much the land surface heats up. And so we go around again in this feedback process. But actually there are still more ways the land and the atmosphere can interact, and it tends to get quite complicated. But I'll just draw your attention to soil moisture and precipitation, which are two things, I guess two ends of the feedback or the coupling, which I'll talk a lot about today. So why are land-atmosphere interactions important? Why might we care about them? Well, I think pretty fundamentally, to predict our climate, we need to understand it. And so we need to understand how the components interact. An accurate prediction, I think, of surface climate is, you need to have realistic representation of land-atmosphere interactions. And so these things are important for forecasting short-term weather, forecasting seasonal hydrological conditions like stream flow, the droughts, heat waves, Australian monsoon variability, as well as predicting future climate. And yeah, improving predictions of Australia's hydroclimate, pretty critically our rainfall, is vital for Australia, I think is fair to say, given our vulnerability to droughts and floods that cause significant effects to us. And in Australia, the value of improved seasonal hydrological prediction has been estimated to be over $1 billion per year for the Australian agricultural sector alone. But despite the potential to improve prediction, land-atmosphere interactions remain poorly observed and incompletely understood. In 2004, a global study by Costa et al., whose main figure is shown here on the top, they found that there to be certain hotspots of land-atmosphere feedback across the world, shown in these sort of reddy orange colours. But you can see there's not much going on down here in Australia, whereas the picture below shows the results using a different method in a different study by Dermeyer et al. 10 years later, which suggests Australia may be in a region of interesting land atmosphere feedback processes. But I guess going back to the Costa figure on top, the fact that, well, these results are for the Northern Hemisphere summer or our winter, which really just reflects, I guess, some of the focus that the study of land atmosphere interaction has had on particularly the US and the Europe to date. Looking at other studies, some past studies have indicated that land atmosphere feedbacks might be more important in controlling Australian temperature rather than rainfall. And also that the exchange of water between vegetation and the atmosphere can affect the intensity of Australian monsoonal rains. And other studies have showed that if you provide numerical weather prediction models with realistic soil moisture and land surface states, it can improve the prediction of surface climate, but again, more so for temperature than rainfall. As for the future, Dermeyer and colleagues in 2012 predicted that Australian land atmosphere feedbacks will strengthen in the future. So this is an image from their study. On the left-hand side, it just shows historical land atmosphere feedback strength, where the blue areas showing areas of strong feedbacks, which you can see Australia is one. And on the right-hand side, this is a prediction for the future. How will land atmosphere feedback strengths change in future, with the blue showing areas where feedbacks are expected to get stronger, including Australia. So the literature suggests that land atmosphere interactions might be important to Australian rainfall, but we're not sure, but it might get stronger in future. So some of the things we're really unsure about here in Australia are which parts of the country exhibit strong feedback as far as rainfall is concerned, and how important are these land atmosphere interactions relative to larger scale processes that we already know have an impact on our rainfall, like ENSO, for example. Do land atmosphere interactions amplify or suppress extremes such as drought and flood? And as far as drought is concerned, you know, while we understand that Australian rainfall is modified by large-scale modes of variability, like ENSO, as I said, the direct physical processes that drive drought here are not well understood. In understanding what causes our droughts to begin persistent and will remain a key concern for Australia, I think it's pretty fair to say, as Australia is projected to experience more frequent and intense droughts in the future. Some of the issues for why there's such uncertainty surrounding land atmosphere feedbacks on Australian rainfall, and actually in most places of the world, are a lack of observations of the relevant variables, difficulty in establishing causation in such a complex and interconnected system. Differences in study approaches have made generalisation hard, and many previous studies have suffered to some degree from model dependency. So I want to know what are the driving processes behind land atmosphere interactions in Australia, and I want to get behind the model predictions and understand the underlying processes, and that has been the focus of my PhD. So if I want to study land atmosphere interactions in Australia, you know, what methods and data sets are available to me? So there's quite a number of methods used around the world to study land atmosphere interactions, of which some are listed here. And they fall into the three broad categories of statistical methods, moisture accounting approaches, and thermodynamic approaches. Considering statistical approaches, of course, there's always correlation, which uses, it says the degree to which the land and the atmospheric processes co-vary can indicate their physical connection. It's simple, it's being used a lot in the literature, and it could be used in Australia with observations of rainfall and soil moisture to look at the continent as a whole. The two-legged coupling index has also been used, not quite as much as correlation, but a little bit in the literature, and it measures the strength of the interaction between soil moisture and evaporative fluxes and boundary layer growth. It's relatively straightforward, but ideally needs to be validated with observations of surface fluxes and atmospheric properties, which are really only available at a handful of field stations in Australia, and the records don't go back very far, so that's an issue. The GLACE index has been widely used in this field worldwide, And it uses climate models to test the strength of land-atmosphere interactions when the land surface is simulated to be coupled or uncoupled from the atmosphere. The method requires complex coupled models, and that, you know, they can produce model-dependent results, as we've seen in the past. And also, it is just the way it's formulated, it's difficult to validate the results to real-world observations. On the other hand, I could use a moisture accounting model to calculate the rainfall recycling ratio, which says that the higher proportion of a region's rainfall that's derived from local moisture, the stronger the land atmosphere feedback. It's somewhat complex, but has the added benefit of giving extra information on the rainfall processes. Isotope analysis can also be used to estimate the recycling ratio, but requires observations that just aren't prevalent here in Australia. Or there's the methods from the thermodynamic category, which all use information on boundary layer properties and how it evolves over the course of the day, and how boundary layer properties are impacted by land surface processes and things like soil moisture to eventually produce rainfall or not. And the methods are pretty complex, and they need high spatial and temporal resolution observations of the land and the atmosphere, which we don't currently have across Australia. So considering those different methods and the data they require, I think on balance, to get a picture of land atmosphere interactions across the whole of Australia and how they impact rainfall, I think correlation can be a good place to start. I know I can make use of available observations of rainfall that we have across the country, and I can combine it with soil moisture and use that relationship as a starting point to, I guess, identify regions of potential land atmosphere interaction that I can then go and investigate in more detail with a more process-based approach, such as rainfall recycling, also highlighted here. But to estimate rainfall recycling, I'd need model simulations of that atmosphere and the land surface that have been validated against Australian conditions, which is luckily available, which I'll go through later on. But I just highlight these two methods as these are the ones you'll see used today. So I've got a plan to use correlation and rainfall recycling to study land atmosphere interactions. I know I've got rainfall, but there's really many data sets of soil moisture. And that's because there's a lot of applications that use soil moisture information, like Australian National Water Accounting, bushfire danger warning, drought monitoring, flood prediction, and all those applications have different ways of estimating soil moisture, whether it be through ground sensors or satellite-based or model-based estimates. And so the number of applications and the number of ways in which to estimate soil moisture has led to quite a number of soil moisture data sets being out there and used, but which of those data sets are most suitable to Australia and most appropriate for my purposes is unknown. So the first part of the PhD asks the question, how does the performance of different soil moisture data sets vary across Australia? Once the soil moisture data is sorted out, it can be correlated with rainfall observations to identify where land atmosphere interactions may be important in Australia. To answer question 2, where do the land atmosphere interactions affect rainfall? And how do they vary in time and space? Presumably, I'll identify some areas of interaction across the country to which I can then quantify their strength in part 3, how strongly do land atmosphere interactions affect rainfall? And lastly, how their strength varies during drought. So what role do land atmosphere interactions play during drought? And all these questions come together to help me characterise land atmosphere interactions across Australia and how they impact on our rainfall. So the first question, first part, how does the performance of different soil moisture data sets vary across Australia? I took soil moisture observations from 3 networks across the country, Cosmos, AusNet and AusFlux, for which some of their sites you can see in the image here, and they span various climate and landscape types. And I correlated those with soil moisture estimated from satellites and models. So I took soil moisture estimates from 3 different satellites, from SMOS and AMSAR2, which are both passive microwave sensors, and the active microwave sensor of ASCAT. And from those satellites, I used various radiative transfer algorithms from different research groups to get different estimates of soil moisture. I also compared the ground observations to soil moisture estimated with some commonly used models, including Waterdyne, which was an Australian landscape an Australian water balance model using rainfall observations or gridded rainfall observations, as well as AURA-L, which is Australia's current water balance model run by the Bureau of Meteorology, a more complex land surface model called CABLE, and 3 simple indices: the antecedent precipitation index, API, which just uses past rainfall as an indication of current soil moisture, and MSDI and KBDI, which are currently used to estimate overall landscape wetness as part of estimating bushfire hazard in Australia. So just to give you a sense of the soil moisture from each platform, here I'm showing a time series of observed soil moisture in black, with soil moisture estimated from the SMOS satellite, using 2 different radiative transfer algorithms, one from a group in France and one from the Netherlands. So you can see that the satellites don't necessarily reproduce the fine temporal scale of the ground observations of how soil moisture varies, but they do manage to pick up the overall temporal pattern. Models, on the other hand, are able to simulate that fine temporal scale of soil moisture as it varies over time, albeit with different magnitudes. But some models are able to reflect ground observations better than others. So for instance, here I point out KBDI in the green. It doesn't simulate soil drying very well, and it dries down much slower than the reality, or slower compared to the observations in black. And it's actually was an interesting result that I highlight because, as I said, KBDI is the current method in Australia to estimate landscape wetness in estimating bushfire hazard. So it shows that if a more accurate method of estimating soil moisture was used, then the estimated bushfire hazard could be different. But that's a story for another time. For now, I'll just wrap up that first research question. And in summary, I took observations from 3 different ground-based networks across the country, and I compared soil moisture observations with those estimated from satellites and models. As far as satellites went, SMOS was pretty great across Australia, especially in the data sparse areas, but comes with the caveat of fairly low resolution. So it gives soil moisture estimates about every 25 kilometres and at any particular point every few days, which is a bit too low for studying land atmosphere interactions, which really vary locally and on the diurnal scale. As far as the models go, Waterdyne was pretty good. It reflected the ground observations quite well and gave us the temporal and spatial resolution that we might want to use in the next research question. But I'll just point out that that work was published in Remote Sensing of Environment, if you're interested. Which leads us to the second research question: where do land atmosphere interactions affect rainfall, and how do the interactions vary in time and space? So where in Australia land atmosphere interactions affect rainfall can be identified by analysing the relationship between soil moisture and rainfall, recalling the simple feedback process I showed earlier. So, but this feedback process can be either positive or negative, it's important to remember. So when soils are wet, available energies petition toward evaporative fluxes, which moisten and cool the overlying atmosphere, which in turn affect winds, turbulence, cloud formation, and ultimately rainfall, which would be a positive feedback. So wetter soils lead to more rainfall, and that process happens over the course of the day. But when soils are dry, there's less moisture available to evaporate, and so energy is petitioned preferentially towards sensible heat fluxes, which warm the overlying boundary layer, promoting a deepening of that atmospheric boundary layer and allowing moisture to reach heights where it can cool and condense and potentially form rainfall, which is a negative feedback, drier soils leading to more rainfall. Regions where more rainfall is recorded following periods of high soil moisture indicate positive coupling, or a one-way feedback, which can be detected statistically when higher soil moisture levels are positively correlated with higher rainfall totals, subsequent rainfall totals. And also regions of negative coupling can be detected when higher soil moisture levels are correlated with lower rainfall totals, or the other way around. But detecting land atmosphere coupling with correlation of co-located soil moisture and rainfall at a grid cell or a point at which we have soil moisture or rainfall information, that assumes a 1D framing of the coupling mechanism. And although soil moisture rainfall correlation has been widely used in the literature, this 1D assumption has been widely ignored. And I'll just run through that now. So if we're going to infer the presence of a coupling with co-located and gridded soil moisture and rainfall, then we're assuming a 1D framing of the mechanism. So we've got a local land surface state influencing the overlying air mass within the same grid cell within the time frame of the evolution of the boundary layer, so diurnally, to produce rainfall. So the assumption requires air masses don't travel through and beyond the grid cell within that time frame. And if an air mass is horizontally advected or transported across the bounds of the grid cell, then the air mass has likely been influenced by the land surface of neighbouring grid cells. And so the 1D assumption inherent in that correlation is broken. So if I am going to analyse the relationship between soil moisture and rainfall on a daily basis, I need to constrain the grid scale to the distance an air parcel might travel across the landscape within a single day. In Australia, wind speeds of around 4 metres per second are most common, as you can see from the PDF here. So for an air mass, I want to know how far is it going to travel in about a day. So if I start at 9 o'clock in the morning, which is when the Bureau of Meteorology rainfall measurements start, so measured in the rainfall in 24 hours to 9 AM. For an air mass to remain in the cell from 9 AM until the afternoon, say 7 hours, then the cell has to be limited to about 100 kilometres or about 1 degree. So I sub-selected the soil moisture and rainfall data with this wind speed threshold to isolate days where the local land surface conditions are likely to be the primary influence on the overlying atmosphere. And in addition to the base 1 degree resolution, I repeated the analysis just to, I guess, check the robustness of the soil moisture rainfall relationship over varying spatial scales. So I included smaller scales of 0.05 and half a degree and a larger scale of 2.5 degrees, but then use corresponding wind speed thresholds of 0.25, 2 and 10 meters per second. So using Spearman rank correlation, I looked at the degree of association between soil moisture using Waterdyne that I looked at in the previous research question, and gridded rainfall observations from the Australian gridded climate dataset over the period of 1979 to 2015, looking at seasons individually and only considering the first day of rain where consecutive rain days were recorded to ensure I wasn't capturing the effect of rain on soil moisture, but soil moisture on rain. And within this framework, I first tested the impact of upholding the 1D correlation assumption, or what impact it has on the interpretation of the soil moisture rainfall relationship. So if we focus on the top row first, here I'm showing the correlation between soil moisture and subsequent rainfall across Australia at different spatial scales going across the columns. And you can see here that by and large, there's a positive correlation or a positive relationship between soil moisture and rainfall, meaning wetter soils lead to more rainfall across most of the country, but with a negative relationship showing up there in the southeast. But if we uphold the 1D assumption, as I have in the bottom row, we can see that when the correlation is properly formulated, the statistical sample size is reduced to the point where there's just no statistically significant relationships found at that smaller scale at 0.05 degrees, which is what the hatching represents. So, you know, if you ignored the assumption, as all prior studies have, then you might conclude that the land and atmosphere are coupled even at very small spatial scales. So I guess my point is that upholding the assumption has implications for how this statistical metric is physically interpreted. Upholding the assumption, we can see that in the plot here that the soil moisture rainfall relationship varies in season as you go across the columns and with spatial scale as you go down the page. At smaller spatial scales, again, the small sample sizes mean correlation can't provide information on the land atmosphere interaction or on the relationship, and so it suggests correlation is not an appropriate metric to be using at such small scales. At half a degree, we can see that a positive relationship is there in Northern Australia in the wet season and transition seasons, but not in winter in the northern dry season. And that relationship is maintained as the spatial scale gets larger. As we move towards the largest spatial scale at the bottom row, we can see a negative correlation emerge in Southeast Australia in winter, which indicates that drier soils lead to more rainfall, which is an intriguing result. But I guess one of the key results here is that when using correlation to study land-atmosphere interactions, the scale really matters. So to sum up that research question, well, as you might recall from the introduction, there's studies that say land-atmosphere interaction isn't really a feature for Australian rainfall. Some studies say it is. I'm saying from here that we can see that particularly in the north and east of Australia, land-atmosphere interactions may be having an impact on rainfall. Particularly we saw a positive land-atmosphere coupling in the northern parts of Australia in the wet and transition seasons, and a potential negative coupling in Southeast Australia in winter. This study, published here in JTR Atmospheres, it was the first to demonstrate the importance of upholding this 1D assumption. And as I said, many studies have been looking at land-atmosphere interaction using correlation. So demonstrating what happens when you uphold or don't uphold this assumption, I guess, means we need to be careful in how we interpret some results and be careful in how we use the method to make sure that we're using the statistical metric in a way that really reflects the physical processes. So yeah, with land atmosphere or regional land atmosphere interactions identified in this research question, the next part of the PhD quantifies the physical relationships driving the interaction. Which leads us to research question 3. How strongly do land atmosphere interactions affect rainfall across Australia? We're going to quantify that strength with the rainfall recycling ratio. So for rain falling, I think you can see my mouse, in any particular region, the moisture for that rainfall can come from one of 3 places. It can come from evapotranspiration within the region itself or the surrounding land, or evaporation transported in from the ocean. And the rainfall recycling ratio is the proportion of rainfall in a region that's derived from evapotranspiration in that same region. So the higher the rainfall recycling ratio, the stronger the feedback. Which is nice, but how do we actually estimate rainfall recycling? Well, I used a Lagrangian back trajectory model that tracked the path of all rainfall over the 35 years between 1979 and 2013. So using information, or 3D information on the atmosphere, for each place where it rained, the model detected how much moisture was present in the atmosphere above, and it tracked parcels of air containing that moisture as they moved through the atmosphere using 3D winds. And as each parcel crossed over a grid cell, the program determined how much of the underlying evapotranspiration from the surface contributed to the parcel's moisture. It records it, and then it keeps following the parcel until all of the original rainfall was accounted for. And this outputs a map of the rainfall's evaporative origin. If you look at the diagram here, it just means that for precipitation with time, we break up the precipitation events into small parcels, and we track those parcels through the atmosphere to see where they originally evaporated from, to give us the information of where the rainfall came from. Now, to drive the back trajectory model, I use data simulated with a sophisticated climate model called WRF, and it's a model that represents the Earth's surface and the overlying atmosphere, which is broken up into layers or levels where equations can be solved. And the modelling project was called NARCLIN, which was a partnership between UNSW and the New South Wales and ACT governments. And the project was developed to provide those governments with climate change projections at spatial scales relevant to them. So the model was run at the 50-kilometre scale, shown in the black box here, for the Australasia domain, as well as at 10-kilometre resolution in the red box for Southeast Australia. The WRF simulation was created with boundary conditions from ERA interim reanalysis from the UK Met Office. And the simulation was spectrally nudged using reanalysed winds and geopotential height above 500 hectopascals in the atmosphere to ensure that synoptic scale systems remain close to the reanalysis. And the simulation provided us with 6 hourly, 50-kilometre 3D atmospheric fields of temperature, pressure, wind and moisture, and 2D fields of rainfall and evaporation that we could input into the back trajectory model. So running the back trajectory model over 35 years and tracking moisture for every rainfall event that happened over the whole country, this is where I found the moisture to come from on average in each season, shown by the colours. So the redder the colour, the more moisture is originating there, and the arrows represent low level wind speed, or the average in each season. So in the first panel, summer, you can see that most of the moisture for Australian rainfall is originating in the more tropical oceans and northern part of Australia, which really just reflects the fact that in summer, most rain that falls in Australia is happening in the monsoonal north. But we also see the importance of the Coral Sea as a moisture source in that season as well, which becomes even more prominent when you move over to autumn. As the wet season tapers off, you see the Coral Sea becoming an even more important moisture source, as well as the land, which directly below autumn there in winter, you can see that the contribution of moisture from the land surface is essentially nil in winter, except for maybe a bit there in the east, with most moisture coming from the ocean to the east and southwest of the continent. And in spring, in panel C there, the contribution of moisture from the land surface picks up again. But yeah, just showing the importance of the Tasman Coral Sea in particular to rain, and this is for rain falling anywhere in Australia. But we can also look at where the moisture comes from for rain falling in different parts of Australia. And I'm just showing some examples here. So we can see where the rain in Melbourne comes from, or from the southeast coast of Victoria, where the Murray-Darling's rainfall comes from, and you can see the importance of the Tasman and Coral Sea there, where the rainfall comes from for Lake Eyre, as well as Sydney and the southeast coast of New South Wales, and Perth and the southwest coast. And these are annual averages. You can also see from this plot the contribution of moisture to rainfall in each of these regions by season. In these pie charts, the light blue indicates the amount of moisture for rainfall coming from the ocean evaporation. The green is moisture coming from the land outside of the region there, and the orange is moisture coming from within the region, so rainfall recycling. And clearly you can see here that the marine contribution really dominates year-round for all regions. Australia typically receives a minimum of 77% of moisture from the ocean in summer and a max of 89% in winter. And we receive a minimum from the ocean in summer because that's the season when the moisture from the land is maximised. And in summer, in the top left plot, you can see the north or northwest of Australia tends to receive about 23% of moisture from terrestrial sources, whereas the southeast of the country receives about 17%. But that the interannual variability of terrestrial moisture was quite high. It was about 6 times more variable than the ocean moisture, which was fairly stable. But yes, it shows that rainfall recycling peaks in summer and is lowest in winter. This plot here in the bottom left shows the maximum recycling ratios in a given season for each basin. So you can see that while it says for Australia, it's an average or a max rather of 24%, which means 24% of rain falling on Australia gets recycled to form more rain on Australia. Broken up by region, we see the northwest recycles the most, and also the Murray-Darling, which is actually one of the higher rainfall recycling rates in Australia outside of the tropics, interestingly. If we look at rainfall recycling in the Murray-Darling a bit more closely, we can see there's a typical monthly cycle of recycling. So on the bottom axis, I've got month of the year, and on the vertical axis, the precipitation recycling. And I've split the basin into 2. So the northern Murray-Darling is in blue and the southern Murray-Darling is in green. And while they have a similar seasonal cycle, you can see that the northern Murray-Darling tends to recycle a bit more moisture, or a bit more rainfall than the southern region. And recycling tends to be highest in spring, summer, around about 9%, but it's quite variable and can be as high as 16 or 17%, particularly in spring. So this means that interannual variability is high, much like Australian climate in general. Land-atmosphere coupling does exert some control on rainfall, which also means that changes to the land surface can lead to less moisture being available for rainfall. Again, looking at the Murray-Darling, the source regions and rainfall recycling ratios did show trends over the 35 years. And this figure shows the change in moisture each season relative to the mean in percent per year. So where you've got blue, you've got a positive trend in moisture contributed by different regions of the ocean or the local or non-local land. And where it's red, it's a declining trend. So we can see that in summer, the Tasman Sea has been providing more and more moisture to the Murray-Darling over time, so the South Pacific Ocean, but the Tasman Sea has been supplying less and less moisture to the Murray-Darling in autumn, and also the Southern Ocean in winter, as well as the local and non-local land in winter. This statistically significant result says that over the last 35 years, less and less rainfall is being recycled to form more rainfall in the Murray-Darling in winter. And looking at all the seasons together, there's been a net decrease of moisture supplied to the Murray-Darling of about 0.1% per year. So to sum up research question 3, the research established the origin of Australia's rainfall using back trajectory analysis, and in doing so define the degree of rainfall recycling across the country in each season. And so that's how I answered research question 3, how strongly do land atmosphere interactions affect Australian rainfall? We can see land atmosphere interactions affect rainfall most strongly in the north, northwest and southeast of the country in summer, and least in the southwest, particularly in winter. The work also characterised the interannual variability of moisture source contributions and recycling. And as I said, showed terrestrial contributions were highly variable compared to marine sources. The research also identified long-term trends in the moisture contributing to Australian rainfall, of which I noted the Murray-Darling. And finally, the research has created a data set for Australia that identifies the origin of moisture for each rainfall event since 1979 and the level of recycling. And that research was published in Journal of Climate earlier this year. Which leads us to the last research question: what role do land atmosphere interactions play during drought? Well, how do we explore such a question? Well, firstly, we need to define drought. So again, I look at the Murray-Darling, but with the northern and the southern regions separately, because as you can see in the middle top panel there, they've each got their own seasonality to the rainfall, with the northern region being more summer dominant than the south. And I look at rainfall in terms of percentiles, so whether it be average, below average, or very much below average, for example. So what I do first, looking at panel D, for the northern region, this is annual rainfall, I find those years with annual rainfall in the bottom decile. You can see that in red. And within those years, I find the seasons below it, in the bottom panel, I find those seasons with below average rainfall in red. And I say the first of those seasons is going to be classed as drought onset, with the remaining classed as drought intensification. And similarly, for drought termination, I find the year of the top decile rainfall following drought there in blue, and I find the seasons of above average rainfall within that year and class them as drought termination. So based on this definition, there were 3 droughts that occurred starting in 1982, 94 and 2002. And I'm just going to show results mainly for the northern MDB now. Well, for each drought stage, continuing method, I should say. So each drought stage of onset, intensification, and termination, I looked at where the moisture for rainfall came from, with the goal of finding out how and why it differed from normal. So as I outlined before, I used the Lagrangian technique to trace the path of moisture for rainfall back in time and space to see where it came from. So for each place where it rained in the Murray-Darling, I traced the moisture in the atmosphere using 3D winds and 2D evaporation, and accounted for moisture gains along the trajectory And this process outputted a map of the rainfall's evaporative origin. Once I identified where the moisture was coming from in each drought stage, I investigated why it differed from normal. So did we get less moisture during drought because those key marine source regions were just evaporating less? Or did they evaporate the same amount? The same amount of moisture was generated, but it got transported elsewhere? Or did we receive the same amount of moisture as normal, but local conditions weren't favourable to the precipitation of that moisture? I also wanted to estimate the degree to which the land surface amplified or attenuated the rainfall anomaly in each drought stage. Did the dry land surface conditions exacerbate the low rainfall, and if so, by how much? So from a moisture perspective, evaporative moisture can contribute to rainfall in a region from 3 sources, as I said before, from the local evapotranspiration or the nearby land, or from ocean evaporation transported in. But to estimate amplification of rainfall by the local land surface, I simply looked at the proportion of the total rainfall anomaly associated with that first source of moisture, which is the local land. Quite simple. So what did the analysis show? Well, firstly, we're just going to have a look at how the evaporative moisture sources changed during drought. I saw a consistent reduction in the supply of atmospheric moisture during the onset and intensification of each drought. So the onset of the 1982 drought was, as you can see here, was characterised by a negative anomaly in moisture from the Tasman and coral seas in particular, which is shown in the orange. So this is an anomaly less than normal, which worsened as the drought intensified and expanded to the Indian and Southern Oceans. We saw a widespread reduction in moisture reaching the Northern Murray-Darling in '94 and during the Millennium Drought. So, less moisture reached the Northern Murray-Darling during drought, which is perhaps not surprising, but interesting that the Tasman and coral seas appear to be anomaly hotspots in particular. And this led me to ask, why did the moisture supply change? We can see from these plots that it wasn't because those marine source regions were evaporating less. So here I'm showing the cumulative rainfall in the first column for each drought in the red drought years compared to the corresponding drought termination years in blue. And obviously, we can clearly see the lower rainfall totals during drought. But in the second column, the marine evaporation, it doesn't really change. So it wasn't that. And yet the amount of moisture in the atmosphere above the region was lower during drought, probably most clearly in the Millennium Drought in panel I. So in 2002, there was a lot less moisture in the atmosphere around the Northern Murray-Darling compared to 2010. And this was even more obvious in the Southern Murray-Darling Basin. So in each drought case that I looked at, the amount of moisture in the atmosphere was a lot lower during the drought years than their corresponding wet years. In the Northern Murray-Darling, atmospheric moisture was sometimes similar between the drought and the termination years, such as in panel G there, which is the 1982, 1983 years. But we can see from the last column that large-scale uplift of the atmosphere was suppressed during drought. So this last column is 500 hectopascal vertical wind speed, which indicates the uplift within the atmosphere. So if air parcels are uplifted to a greater altitude, they can cool and condense where they can form rainfall. So for a similar amount of moisture between 1982 and 1983, you can see here in panel J that uplift was greater in 1983 compared to the drought of 1982. So even though there was a similar level of moisture for that particular drought, it suggests that there's a lack of precipitation generating mechanisms able to lift that moisture and precipitate it out during drought. And it may be due to a reduction in the local convective activity, since recycling ratio was also reduced in drought. That's something that needs looking into further. So I can say that the reduction in moisture supply during drought wasn't due to reduced evaporation in those key marine source regions, which means that the same amount of moisture was generated, but it was transported somewhere else. And this is exactly what we can see here when we look at the anomalies of the low level wind speed during the drought onset and intensification stages, winds shown by the arrows. So we can see anomalies in the regional atmospheric circulation moving away from the Murray-Darling, for example, in the onset to the 1982 drought, the first panel, and the next panel becomes more obvious during the intensification stage. So the easterlies are pushed to the northwest and the westerlies to the southeast. And this is sometimes associated with anticyclonic circulation. As you're probably aware, there's often a high pressure system sitting over the region during drought. And we can see a similar pattern of moist air being directed away or out of the region in 1994 and during the Millennium Drought. And this situation reversed during the breaking of each drought. So in all three drought break cases, anomalously strong easterlies advected moist marine air from the Tasman and Coral Seas over the Great Dividing Range into the basin, which could then contribute to rainfall. And this says, I think, that we need to better understand this easterly flow of moisture and investigate its variability, including the impact from synoptic scale systems and large scale modes of climate variability, particularly during drought and the ends of drought. So I've been focusing on the ocean to the east of Australia quite a bit so far, but of course the land surface also played a role in the rainfall anomalies, as you can see here. So we can see from these plots that less moisture than normal was contributed to rainfall during drought, which perhaps not is surprising given that the land surface was drying out. But by how much did the land surface exacerbate the low rainfall situation? And for that, we return to the measure of land surface amplification that I mentioned. And we can see here that the terrestrial anomaly accounts for up to 6% of the rainfall anomaly across the drought stages. The moisture anomaly from the land outside the northern basin makes up a large proportion of the total rainfall and so has a greater amplification factor than the local land. But the ocean is by far the largest contributor to the rainfall anomaly as far as the moisture is concerned. And yeah, it just really reflects the overall dominance of the ocean evaporation to the moisture supplying regional rainfall. And therefore, this estimation of the relative roles of the local land and the remote ocean processes is very much from a moisture perspective. So to sum up, what have I learnt from research question 4? I can see that droughts in Southeast Australia have distinct signatures in terms of the moisture that either reaches or doesn't reach the region. And this appears to be mainly due to atmospheric circulation anomalies redirecting that marine moist air in particular from the Tasman and Coral Seas. And this suggests that we need to investigate the impact of synoptic systems and large-scale modes of circulation on the relationship between the easterly winds, the moist advection and rainfall during Southeast Australian droughts. The results also showed that drought in the northern Murray-Darling wasn't solely due to a lack of atmospheric moisture, but also from a lack of mechanisms able to precipitate what moisture was already there. So we also need to investigate the mechanisms responsible for the suppression of rainfall during drought in that region in particular. And this work was published in Geophysical Research Letters this year, if you want to see more. And with that, I'll sum up by highlighting the contribution to our understanding of land-atmosphere interactions in Australia. As I said a couple of times, the progress of land-atmosphere science in Australia, like many other parts of the world, has been challenging due to the lack of long-term observations of the relevant processes. Observations like soil moisture underpin many of the methods used to identify and quantify interactions. And this thesis, the first part, extended the geographic coverage of comparison of soil moisture to ground observations to 3 networks across multiple climate zones and brought together particular estimates from satellites and models for the first time. And that soil moisture comparison work really just informs applications beyond the study of land-atmosphere interactions as well. The PhD demonstrated that the state of the land surface does impact on Australian rainfall, most clearly in northern and southeast Australia, but again, it depends on the spatial scale you use. And yeah, in terms of that correlation, it really was meant to be a fairly quick assessment of the soil moisture rainfall correlation, but it ended up critiquing a commonly used metric in the field and demonstrating the importance of correctly applying it to really reflect the physical processes it's meant to represent. The PhD quantified the regional and seasonal influence of land-atmosphere interactions on rainfall using rainfall recycling ratios. showing it to be strongest in northern and southeast Australia, particularly in spring and summer. And the work carried out to compute rainfall recycling had the co-benefit of identifying the origin of rainfall in each part of Australia for the first time. And this allowed me to analyse the role of land-atmosphere interactions during drought and to determine their importance relative to larger scale processes. And interestingly, I was able to show in the PhD how droughts in the Murray-Darling evolve and terminate through evacuation of moisture from the Tasman and Coral Seas. So in conclusion, land-atmosphere interactions do affect Australian rainfall, most strongly in spring and summer in northern and southeast Australia, but play a secondary role compared to larger scale processes in drought. Future work might consider examining the sign of the feedback between the land and the atmosphere in southern Australia in winter. For this, I'd say sub-daily analysis is needed to examine how the vertical profile of the boundary layer co-evolves diurnally with the land surface to result in rainfall being promoted either by wet or dry land surface conditions. And this could be done using a thermodynamic approach, such as convective triggering potential, for example, using remotely sensed information on the atmospheric profiles with simultaneous land surface observations. And that's really going to help us understand how to model land-atmosphere interactions in terms of climate prediction in this part of the country in particular. I think we need to prioritise the understanding of the relationship between synoptic scale circulation and moisture advection into the Murray-Darling during drought, and how that relationship is modified by large-scale climate variability and terrestrial processes. And lastly, it also needs to be established whether any of the current generation of climate models, including Australia's ACCESS, whether they can simulate droughts of Southeast Australia with the signature and the relative role of marine and terrestrial moisture sources and the mechanisms identified in this PhD. With that, I'll say thank you for listening, and also thank you especially to my supervisors, Albert, Jason, and Andy. Thank you.
Chiara, can you hear me?
I can.
Wonderful. Thanks for sorting that out, Pete. Congratulations on a great presentation. And first of all, I suppose, as you've shown already, all this research is already accessible in 4 excellent articles. So if people have kind of nitty-gritty questions, don't really want to ask about it, they can potentially find their answer there. But let's see if there's any questions based on your presentation. So if anyone's got a question, you can put a comment in the chat, or you could take a punt on starting to talk, and we'll see if people interrupt each other. In the room here, any questions? There's always that first question where no one dares. Yep.
This is not directly related to your research, but I do remember from about the beginning of the millennium drought, watching the Bureau of Meteorology forecasts coming through, that time after time, belts of clouds that they had assessed as containing X amount of moisture and therefore would deliver so much to the eastern states would just, you can watch it on the coverage map, the clouds would just dissipate as they came further to the east. So at that time I was assuming that there was obviously some sort of mechanism from the ground that was just drying up these otherwise. And what the models from the 80s and 90s had said was any of those moisture clouds that came in would deliver rain, and yet time after time they just didn't.
Yeah, that was an interesting result for me as well. I guess having seen, as you said, time after time, those synoptic maps that you see on the news with the cloud band, the northwest cloud bands coming across, I did expect to see some moisture coming from that direction. But what is happening, so based on this research, which showed the moisture for Southeast Australia is really coming from either the east or the south or the southwest, not from the northwest. I think it ties in with some previous work done by Kim Reid from Melbourne, who looked at these northwest cloud bands and showed that on the days when there is a northwest cloud band, there's often a high pressure system sitting to the north, so around Queensland or thereabouts. And so this anticyclonic circulation sometimes pulls moisture in and down, so in from the Coral Sea and down into the southeast, where it comes into that northwestern trough and gets uplifted and turns into rainfall. And so I think that's why often the northwest cloud bands are, associated with rainfall in the southeast, but they don't necessarily represent the source of the moisture, rather just a mechanism that help the moisture be lifted and precipitated. And I think often those cloud bands are high as well. They're not necessarily low rain-bearing clouds.
Quick one, and that was that during the actual worst of the first 4 or 5 years of the drought, even the ones that drifted over from the Southern Ocean weren't associated with that northwesterly flow. They also dried up very substantially as they entered from south. So just another reason for that must have been something else.
Yeah, the time of year matters a lot as far as the moisture for rainfall. So I think when those westerlies in winter, I don't know if you remember, but from the figures I showed with the wind speed vectors, if there is a high pressure system sitting over the southeast, then those westerly winds are going to be redirected more to the southeast. And so any moisture coming across kind of gets deflected. But yeah, it depends on the time of year.
Other questions here in the room or online? Oh, there's Marvin's got a question. Thank you so much for a great presentation. My question is, what is our best interpretation of the negative feedback between soil moisture and rainfall in Southeast Australia?
I don't know if it's our best interpretation, but it's my interpretation currently. I think what may be happening is this correlation, so of soil moisture and subsequent rainfall, may in fact be not necessarily be reflecting a negative coupling. It may be reflecting that it was going to rain regardless of the soil moisture. So in winter, if we're getting sort of westerly frontal systems coming across, they may rain out regardless of what's happening with the land surface. Or they might rain out preferentially over dry soils. I don't think we can say either one from correlation. And that's why I said we need to, if that's something we're interested in really characterizing properly, then we need to go in with more process-based, data-driven methods to be able to say whether it is a true negative feedback or whether it's just representing, whether that correlation relationship was just representing the fact that in winter we get these large-scale systems that bring rain, regardless of the soil moisture.
Thanks, Chiara. And maybe as a little add-on, a negative feedback like that has been hypothesized and arguably demonstrated, or at least evidence presented before. So it's not something that you kind of pull out of the air, so to speak. It's not impossible.
No, it has been shown for other parts of the world. Yeah, particularly with clouds forming over drier soils or forming over wetter soils, but then being physically displaced and raining out over the drier soils, which would lead you to detect a negative relationship. So it's tricky and it's easy to get tied up in knots with causality, but there I think are methods available that can help you untangle those feedbacks. But yeah, you need some good data.
Other questions? Last takers, either here or online? No? If not, then I guess I would like to commend you on a perfect PhD project, Chiara, perfectly executed from beginning to end. Also a great learning journey for me personally. being atmospheric scientist. It's wonderful to have you working with you and the two supervisors, Andy Pittman and Jason Evans, on this. Many an interesting discussion was had, and I personally learned a lot from those discussions, but also from your approach to doing your PhD. And I would present it as a model for those who can follow or try to follow in your footsteps and take that approach. You've been an excellent example, I think. So congratulations, of course. We'll be submitting very soon. Did I hear somebody online who wanted to add to that? Jason or Andy, were you wanting to say something there, perhaps? Oh, okay. We can't easily do that. We cannot hear you if you speak. That's terrible, Andy. Okay, we're getting some congratulations from I'm sure Andy will get another opportunity to provide his commentary too. I do apologize. I assumed everyone could put their questions in. Unless it's a very quick process, I think we'll leave that because we are kind of over time already. So we might just leave it for now. Apologies to those who couldn't speak. Jason also says congratulations. Well, we can all read it as well, so I don't need to repeat this, do I? So on that, I would say thank you very much and congratulations a little bit maybe early since your PhD hasn't been examined yet, but I think it's safe to say. And thank you for a great presentation here. And yeah.
Thanks for listening.